so. I think it's good to be provocative. That's what we wanted to do with the book, is present those kinds of questions you could have about the universe. The why questions, of course, are always somewhat dangerous questions to head into, but I think the where you can talk about it as being based in physics, right? I mean, I want to understand the physical process by which our universe came into being.
Any sufficiently advanced technology is indistinguishable from magic.
Professor Geraint Lewis, who is, I believe, an award-winning astrophysicist. He is a professor of astrophysics at the Sydney Institute for Astronomy. And I've been told, I had on somebody recently who was Australian. Actually, I had a few Australians. I had Brian Schmidt on. He's American. And then I had somebody else on, and I said down under, and they said, you guys don't like that. Although you're not originally Australian, if I recall correctly. You're British, right? I'm
British. I've been in Australia now for the last 22 years, though. So I'm a citizen. But yeah. I don't mind the phrase down under. We are a long way from just about anywhere else.
Yeah, that's true. Yeah, I've noticed many times that it's the place that people most want to visit, but kind of have put it on their bucket list for later after the pandemic subsides. May that come soon. And today we're on the podcast. You were last on way back in 2020 with your co-author. I believe was he your student, Luke Barnes?
He was originally my master's student, so that was a long time ago.
And Luke, and you were on last time for the Cosmic Revolutionaries Handbook. That was a lot of fun, that book to read and to go over with you. We did a live stream. You guys can find that way back in the archives of the Into the Impossible podcast. But today we're on to talk about this magnificent new book called Where Did the Universe Come From? Which immediately, like Cosmic Revolutionaries Handbook, I think you're a master at titles. And we always like to begin conversations with authors with a segment that we call Judging Books by Their Covers. So we have now to do what you're never supposed to do, which is to assess a tome by its plumage. Where does the title come from? And where does the cover image and illustration come from? And first, we should mention this was written with your co-author, Chris Ferrie. Is that how you say his name?
Yes, Chris Ferrie, who's at the University of Technology in Sydney. So like all these things, titles and covers are now workshopped a lot, right, with your publisher, because whatever your original title is, they talk to people and they sort of say what grabs your attention. And as you know, this entire scientific book market is quite a busy marketplace these days. And I think that there's a feeling amongst the publishers is you've got to have a flashy cover, you've got to have an attractive plumage if you're going to get anybody to pick up the book. And I feel like when I go into a bookstore now and I just see the wall of science books, and even I stand there going, I don't even know where to start anymore.
Yeah. A couple of years ago, the fad was to have very dark and ominous covers. This one's kind of dark, but not as dark as other covers. Your last book, Cosmic Revolutionaries Handbook, is bright with a fist raised in the air, anticipating, kind of the reaction that many would have in delight, raising and pumping their fist in the air. But this one is kind of evocative, maybe the galaxy, maybe some weird waveforms. And I guess I want to start with the title, although, as you say, authors rarely have a chance to contribute to the cover art or the design, but sometimes they let us choose the title. But maybe in this case, the question I most have is that W question, the where question. I've heard said you should never ask questions about that begin with why, W-H-Y, in science. I never heard, an opposition to using where, though. What does it mean, where did the cosmos come from? Doesn't that presuppose there was a something, there was a time, there was a cosmos, proto-cosmos? Isn't this quite provocative to start a book with such a question?
I think so, and I think it's good to be provocative. That's what we wanted to do with the book, is present those kinds of questions you could have about the universe. The why questions, of course, are always somewhat dangerous questions to head into, but I think the where you can talk about is being based in physics, right? I mean, I want to understand the physical process by which our universe came into being. Now, I like many books that start with a question doesn't necessarily mean we've got all the answers inside the cover. But of course, you know, and your listeners know that there's more than one single idea about where the universe came from, and was there a before, or was there a universe from nothing? And we just wanted to bring some of those ideas in because the sort of central theme of the book is bringing together notions of cosmology, the large-scale universe, with notions of quantum mechanics, which is often the small-scale universe. And of course, that where did the universe come from is tied up in the two of them somehow, and that's what we've still got to work out.
And when I look at kind of some of the subheadings and the chapters, it's a small book. It's a dense book. It has lovely illustrations and a lot of good humor. And I think, it presupposes a lot of the questions that we as working cosmologists get asked. And yet it doesn't fully leave the reader with the sense that everything's known that could be known. In fact, there's a chapter that you entitle towards the end, do we know everything, or will we ever stop running out of things to learn? Now, I never like to give away the ending of the book, especially when it's like a novel. I had on Chris Hadfield, the astronaut who wrote a murder mystery, and that is really hard to interview somebody about a fiction, but here it's less controversial. So let me ask you, isn't it true that, as Wheeler said, kind of the more that the island of knowledge expands, the more the boundary, the coastline of ignorance also expands. But of course, area increases, more rapidly than boundary. But are we learning more than we're revealing our ignorance about, or are we really, kind of losing the game against this infinite ocean of ignorance?
Oh, I mean, that's such a tough question to answer. I mean, I am reasonably sure that that we will never stamp our fist on the table and say, right, we're done. Physics is done. We now know everything. Because even if we get hold of that theory of everything that people have spoken about now for almost 100 years, right? There will still be so many questions there to solve. So we will not know everything, but I do feel confident that we will know more. I mean, that's definitely certain. But as you said, the shoreline of ignorance that is going to continue to expand. And I have a feeling that some of the things that people say are outside the bounds of science today and of metaphysics, etc., those things are going to be drawn in. Questions of like, what was before the universe? Are there other universes out there, etc.? They might become mainstream science down the road, but it's very hard to predict the future, right?
Mm-hmm. Yeah, and especially, that's what Yogi Berra said, it's tough to make predictions, especially about the future.
Yeah.
Now, some of these questions do have well-defined answers, and I think as scientists have learned more and more about different topics, especially you think about the life in the universe and so forth, which maybe we'll get a chance to get into. But certainly in the stellar astrophysics, the notion of the lifetime and the lifeline of stars, black holes, etc. These are becoming more and more precise and accurate as we develop. And yet, the more that we dig down deeper into the theme that really runs and resonates throughout this book is kind of this overarching notion of the quantum. And I don't know if that was intentional, but the book is kind of, it seems to me like a primer. It's portraying and parlaying our notions of classical mechanics and classical astrophysics into what we don't know, which is largely in the quantum realm. And there, I feel like it may be kind of hopeless, but as you can hear any kind of quote that you like, but Richard Feynman, anyone who says they understand quantum mechanics, doesn't understand quantum mechanics. And with the proliferation of books about the interpretation of quantum mechanics, different schools of thinking on quantum, do you feel like quantum mechanics needs to be really refined and understood before we can have quantum cosmology, quantum properties of black holes, for example? Do we first need to make basic bedrock advances in quantum theory that we teach to undergraduates before we can build onto it a scaffolding to go into applications in astrophysics?
Yeah, so that is one area that I wanted to try and sort of stay away from slightly, was the overall interpretation, because we know that whilst there are varying interpretations, the mathematics works exceedingly well, right? But you have to let something go in your sort of common sense to come up with a description of just what is really happening. What are the mathematics really describing? And I do feel that something has to change somewhere with our overall philosophical understanding of quantum mechanics. I feel that that people have been shouting at each other for many years about what the right interpretation is. I actually just went and reread an old book by John Gribbin called In Search of Schrodinger's Kittens. I'm not sure if you've read that one.
I remember that. I don't know if I read it, but yeah.
But the final couple of chapters settles on this description of quantum mechanics, which comes from Feynman and Wheeler, of course, the transactional idea, where essentially quantum mechanics works because signals are sent backwards and forwards in time, right? There isn't just this forward propagation. Things talk through time. And of course, the mathematics all works, etc. But that interpretation just makes everybody feel really uncomfortable. It doesn't sound right that you get signals traveling through time. But the universe doesn't care about what we feel is right? It's just the way that it works. And I still don't know what needs to be done, though, for one interpretation to be separated from another to say that this is the better description of quantum mechanics. But I do feel like something needs to happen. Even though it's very, very successful, something's waiting in the wings that will change the way quantum mechanics will be thought about and applied. So we will get towards that theory of everything, such that we can talk about the quantum aspects of black holes, the quantum aspects of the birth of the universe, etc. Those things which are currently hidden from us.
Yeah, and sometimes I push back, as I will with you, with respect and dignity that you deserve. But even with Roger Penrose, and I'll say, look, the only times we talk about things where we need a quantum theory of gravity have to do with singularities and black holes and the origin of the universe, if there was a singularity, which many people dispute, including Sir Roger, right? So what do you say to people like that yes, there is a great hope that we can unify quantum mechanics and gravity, but there's no letter from God or from Zeus or I don't know, whoever, from Oz, I don't know, there's no letter that guarantees that we have to unify them. So do you feel like there is kind of an overabundance of these theories of everything, unification? There's half a dozen or more that I can point to just on my channel alone. But is that really kind of the richness? Is it an overabundance of riches in that one aspect of physics versus devoting it to all the quantitative? There's no need for quantum thermodynamics or some new interpretation of thermodynamics. Works quite well and it's featured in the book. So do we have an oversupply and under demand for these theories of everything?
Oh, so again, I think I'm going to tread carefully here, right? Because I think I actually think there's a couple of things with the theory of everything, right? So firstly, there would be the personal satisfaction that we could crack that problem, if it can be cracked. We don't even know if there really is a theory of everything, right? But if it was, physics would sort of go, oh yeah, look how smart we are. We've actually worked this out. But as you said, there's more than one contender on the table for a theory of everything. But in terms of the physics effort worldwide, this makes up a tiny fraction of a percent of the effort. Most physicists around the world are solid state physicists, etc., working on practical problems every day. Mm-hmm. They probably don't think about or even need a theory of everything. So I don't think we're putting a huge effort into that area. I think that area gets a lot more attention from the media than the effort actually generates. But of course, one of the other things is if we get this theory of everything, right? If it exists, and we do say, oh, I now understand the center of a black hole, and I now understand the start of the universe. That doesn't mean that it won't open other doors to our understanding about what's going on in the universe, right? We have this overall picture about, let's just take cosmology, right? Standard cosmology written in the language of Einstein's general theory of relativity. And as cosmologists, we use this stuff every day, calculate distances, redshifts. We're all happy with it. And we know that it can't be complete because there isn't quantum mechanics in there. And we have mysteries out there. And some people have claimed, right, that dark energy and dark matter is the fact that we've got relativity wrong, that we are missing something in relativity. And I'm not in that particular camp, but there is a vocal group who are. And if we have that overall theory, we should be able to say whether or not dark energy is an illusion because we've forgotten something quantum mechanical in cosmology, or if it's a substance that's out there in the universe that we should go hunting for. So there should be other questions that we can solve, hopefully. But again, we're trying to predict the future here, and we know how difficult that is.
Right. So one of the themes that runs through the book has to do with symmetries and kind of guiding principles. But where I often, find the subject matter sort of lacking is that we really care about the broken symmetries. As you point out in the book, you and Chris point out that they're perfect symmetries. We wouldn't be here. Almost every symmetry has the capability for being perfect, and yet if any of them were, I think we wouldn't be here. So let's take matter antimatter symmetry, and there is thankfully a part per billion level asymmetry. Again, we believe we're made of matter, and but that's arbitrary. We could call ourselves matter, but we're really antimatter. It doesn't matter. No pun intended. The opposite symmetry isn't perfect. You had a nice Twitter thread that I kind of used in one of my videos, solo videos on my YouTube channel, about the maximal violation of CP violation. I think you go through it in the book, and I wonder if you could take the readers through it as well. What is CP violation? What does it mean that it's violated? Unlike, say, electric charge, which we don't believe is violated. We think there's symmetry between positive and negative charges, and locally between matter and antimatter. But what is violated? What is CP violation, and why is it so important, both to our existence, but also guiding principles in physics in general?
Yeah. So this is again the symmetries thing. I think this is one of the most beautiful things in physics, which most students don't get to see until their later university years. And even when I first encountered symmetries and breaking symmetries and all that kind of stuff, it didn't really hit me about what was being said here. And it was only a long time after that I suddenly realized how important this is, right? You get to Neutrinos theorem and you suddenly go, that's why something's conserved. Now I understand that. So you've got our universe, you have stuff in it, and you can ask about doing particular transformations, right? So symmetry transformations. So, you can replace, you can take all the positive charges and make them negative, take all the negative charges and make them positive, and you'd sort of think, right, everything should work out to be the same, right? We've arbitrarily labeled positive and negative. Everything should work out to be the same, right? So with electromagnetism, that doesn't really matter. We're also with gravity and the strong force, perfectly happy when it comes to flipping around charges, etc. The one where things get really weird is, so the C in CP symmetry is charge symmetry, if I change positive to negative. The one where things get really weird is the P, which is known as parity violation, right? So we're talking about another symmetry. And again, this was all done in the 1950s, and I think it's a huge disservice to physics that we don't talk about this a lot more, is that the work that was done by Yang and Lee in terms of the theory and Wu in terms of the experimentation. So essentially, all parity violation is you say to yourself, right, I look at the universe around me, it's all behaving the way it is. And if I imagine that instead I was looking at the universe, but viewed in a mirror. So I'm just watching a mirror flip. You would expect that the view that you see in the mirror would be perfectly fine. It would all be very happy. And you would say, right, everything that's going on in the mirror, that I can expect to see that in this universe. Except when it comes to one of the fundamental forces of nature, and that's the weak force. So the weak force is, it's in there in the mix of strong electromagnetism and weak. And so they're like the quantum forces. And you also have gravity. And what Yang and Lee basically suggested is that they looked at all the evidence for weak interactions, and they said, well, it doesn't, the weak force doesn't seem to need to obey this parity symmetry. I.e., if I have an electromagnetic interaction and I look at it and I look at it in a mirror, both are physically things that can occur. But if I take a weak interaction and I look at it in a mirror, the version that I see in a mirror is something that doesn't actually occur in our universe. And this is what Wu showed in her famous experiments, is that she was looking at the decay of, I think it's cobalt into nickel, right? So it spits out an electron or a positron. So it's a weak sort of process. So what you get is you get your big nucleus spinning, it spins in a certain direction, and it tends to spit the electron out in a certain direction, and a neutrino comes out in the other direction. And when you look at that in the mirror, that's not something that occurs in our universe. So the weak force basically breaks that parity violation. It breaks that parity symmetry. And again, that's rather earth-shattering, because in your mind, why should the universe know about whether or not something has an acceptable view in a mirror or not? Essentially, what you're saying is that the universe knows its right from its left, which seems very weird when you think about it. So, there was a hope that if you had a charge symmetry and a charge transformation and a parity transformation, that would give you back a view of things that occur in this universe. So not only do I look in the mirror, but I change all the positive signs to negative signs, etc. That should get me back to what I see in this universe.
Right. A simple example would be a wire that has current flowing through it. If you reverse the charges, so now it's electrons are running instead of protons are running through it instead of electrons. But you also have to reverse the direction that those objects are traveling. You'll get the same amount of charge traveling per unit time.
That's right. So everything then works out. But of course, then there are experiments that people have done now to show that that combination of C and P together, and the experiments are kind of involved, but when you sit down and you work through them, you sort of find that even that C and P are violated in certain experiments. And again, you have to wonder, why is the universe fractured in that way, right? There's a fracture in there, and it's written somewhere into the laws of physics. It didn't have to be there. The universe could be perfectly symmetric in that particular two quantities. And now, of course, there's a hope that it's a charge transformation, a parity transformation, and a time transformation. So you flip everything in terms of time, that will restore everything in terms of what I see in my mirror and what I see in the universe. But it's not guaranteed, right? It's not guaranteed. There's a hope that CPT is going to be perfectly symmetric. And I think it's what, we are almost headed off into the realms of that metaphysical area, right? Why is the universe this way? But to me, it is a somewhat uncomfortable kind of thing, in that we know, as you said at the start, if our universe was perfectly symmetric, so it was born with no matter at all, we wouldn't be here, okay? So there's a 1 part in a billion that a symmetry between matter and antimatter that allows us to be here. If that difference of 1 part in a billion was also there in charge conservation, the universe would be a complete mess, right? If charge could appear and disappear at random around the universe, things would be highly chaotic. So why is charge perfectly symmetric and matter slightly fractured? Right. And we just don't know the answers. We can write terms into our equations, but we don't know why it's that way.
Yeah, exactly. So what's so fascinating about these, broken symmetries is that in the case of matter antimatter, as you just said, if there were equal amounts, we wouldn't be here. And the amount of violation is incredibly small, and that allows us to be here. And we can ask, well, what if it was, even more maximally violated? We would get to the standpoint that we may not exist either. In other words, it's dangerous to invoke things like anthropic or existence proofs, but the fact that we exist has to be taken into account when assessing some of the likelihood of these laws to actually be valid. Now, in the case of the parity violation, in your string of tweets that kind of motivated me to include in my video about Madame Wu, Shinsen Wu's famous experiment that validated less than a few weeks after Yang and Li came up with this prediction. I'll have a link to the video up here somewhere. But that I go into talk about that parity is violated maximally. And you go into detail as to why that is. I wonder if you could recapitulate that for the listeners.
Um,
What does it mean to be maximally violated?
well, it's not just a subtle effect, right? When you look at the weak interaction, it's just blatant. It's not like you look in the mirror and it's 1 in a billion events looks like it doesn't obey parity. It's every single time. So when I take my mirror view of the universe and look at the weak interaction, it disagrees with what I see in my universe. So it could have been subtle, right? It could have been so subtle that it could have been just 1 decay in a billion would look weird, but it's not. It's every single one of them. So again, why is parity violated at that particular level? And again, and where is this written into the fabric of the universe?
Right.
Where is it? Where does the universe need to know that it definitely has a right and definitely has a left? Not a little bit right and a little bit left, but definitely right, definitely left. So it is again one of those deep mysteries that does bother me somewhat. It keeps me awake at night.
Yeah, it is fascinating, and that these, at some level rely on these particles, which you also talk about in the book, these neutrinos, and how stunningly important they are, even though by far a million times less massive than the most massive or least massive other particle, the electron. And I always get kind of tired of it, like Carl Sagan saying things like, as much as I love Carl and respect him, I've had his widow, Ann Druyan, on the podcast, his daughter, Sasha Sagan, on the podcast. So I have utmost respect. But he would say things like, oh, you look into the cosmos and see how insignificant we are. So what size scale would we be important? Like, is Jupiter important? Is a neutron star? Like, what level of size do we have to be? If, as you point out, neutrinos are these insignificant ghost particles, and yet they play this inordinate amount of a role in the composition of our universe. So maybe can you wax poetically about what neutrinos mean to you in the cosmos, including these symmetry principles, which they seemingly uniquely reveal?
Yeah. So yeah, neutrinos again. Again, my deep down sort of wish, about the universe is that really that neutrinos hold the key. That they even though they are seemingly inconsequential particles, there's something about the neutrino which is telling us something deep about the universe. So you mentioned about parity being maximally violated, right? So we know that we have lots of different kinds of particles in the universe, and the neutrino is not that dissimilar to the photon, the particle of light. The neutrino's got a teeny bit of mass, the photon's got no mass. But the photon, it also has spin, and a photon can spin this way and it can spin that way, perfectly fine. It's symmetric in terms of its parity, right? You look at a photon in the mirror, it's spinning in the opposite direction, that's fine. I've got photons like that in the universe. Neutrinos, though, always spin the same way, right? So, and I can never, I might get the right hand and left.
I'll teach you how, Geraint. You ready?
Yeah.
So light, that the double helix, which we'll get to in a minute, DNA is life, right? Life is always right. Life is always right.
Okay.
And then neutrinos are always the opposite of life. So neutrinos are only left-handed neutrinos and right-handed antineutrinos, and DNA is only right, and there is no left-handed DNA. Go on. That's my helpful mnemonic to teach you.
Okay.
One of my favorite professors. So I feel good now.
Okay, good. So the reason that Wu's experiment showed the result that it did is that neutrinos are always born left-handed. They're always born with the same spin. And again, you can ask yourself, what tells them when they're born that they all have to spin in this particular direction, and all antineutrinos spin in the opposite direction? And it's somewhere there in the weak interaction. And what we've had to do with our mathematics is we've basically had to write that in, right? We've had to write that all neutrinos are left-handed, all antineutrinos are right-handed. But that spin, as I said, gives a definite handedness to the universe, right? It does imprint a handedness because everybody would agree that all neutrinos are spinning the same way. And there have been links between the spin of the neutrino and us being alive here on the planet, right? Because we are handed creatures, right? Our molecules tend to have a preferred handedness to them. And so you can have a molecule that looks like this, and you can have the same molecule, same atoms, etc., but the mirror image of it, and your body will use one and it will ignore the other because you are built out of molecules with a handedness. And people have suggested that the reason that we have this handedness to our molecules is due to the weak interaction occurring somewhere in the early universe or in the early life of the Earth that basically twists molecules in a certain way. Lots of hand waving involved in all of this. But we might be here living the way that we are living because of this fundamental aspect of the universe that it knows right from left, which is...
I made a video about that too. I'll put that link over here somewhere too. Yeah, the life and the weak interaction. Yeah,
it's an intriguing story, and again, my hope is that at some level that there's some truth in that. Of course, there are lots of people that don't like to tie fundamental physics to life in that manner, and there's lots of things about whether it was polarization in early star forming regions, etc. But I do like the notion that we are essentially the weak force writ large at some level, right?
Right. And that the weak force is responsible for us living. And again, it's also kind of maximally violated in that we only see one form of DNA and we only see one form of neutrino. So yes, but it's dangerous equating, two things that are equal except for those that vanish or something like that. Yeah. All vanishing, all zeros are equivalent. So getting back into the book, what's so, kind of delightful to me is that it kind of picks up in some sense where the previous book left off. In other words, last time you were kind of concerned with, well, if somebody writes to you or to me and says, Professor, I've got this great idea and, the way the universe was born and it doesn't involve any of the known laws of physics and I'll share my Nobel Prize with you, Professor Lewis, but you got to help me with the math. Et cetera. And then you come up with this rubric, or which you refer back to Michael Keyes and his paper systemizing the theoretical virtues. I wonder if you could do the same, for some of the more speculative things that you talk about in the book, such as the theory of everything, such as entanglement and the kind of more speculative aspects of physics. Where would these fare? As a cosmic, revolutionary, how would this book fare against the previous book?
well, okay. So, the goal of this book, of course, was to try and present how we actually understand how things work, right? So there are various complicated things that occur in the universe where you have gravity and quantum mechanics, and they're doing their stuff to make things like stars and the expanding universe, etc. What we didn't want to do in too much detail in the book, though, is go into how we know those things are the best description, right? We didn't want to write a history of the development of the modern theory of stellar evolution, etc., because that's already been done. So this was to tell people, like, this is how we understand things work at the moment with the theories that we have. But as you mentioned, we wanted also to get across that the story isn't over. We haven't got all the answers yet. So at some level, I guess there is a bit of an invitation in there for people to think about, what would be the next step? But what I would hope is that they would go back to our previous book and understand that if they do have a new idea, that there's a process by which you go through, if your idea is scientific, for it to, have an impact on the community rather than writing surreptitiously to various professors offering shares of Nobel Prizes.
And I kind of could comment on with that is always this question of, who is doing what? So someone's asking, where did the universe come from? Can it be answered? Can it not be answered? We had Paul Davies on recently about what's eating the universe. We've had on Mario Livio off of why, so all these questions, right? But those always presuppose some kind of consciousness and some sort of entity. And even, notwithstanding the difficulties of quantum mechanical interpretation, still the notion of consciousness and its role with regard to, can we recognize the theory of everything? I've heard people say, if life existed in the universe, Paul talks about the shadow biosphere and things like that. Maybe it's right in front of our face. Maybe we have it already. Is there any danger? Like, do we have just an impediment to possibly not seeing, answers to certain questions because we don't understand the role of this ultimate observer, this 3-pound supercomputer, in our heads, the role of consciousness? Or can we divorce consciousness from, the observer from the observed, and then, in so doing, answer these questions, these ultimate existential questions?
This is something that I've churned over in my mind a lot in the last couple of years. So the 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 supercomputer in your head, we've come an awfully long way in the last few tens of thousands of years, right? And at some level, it is rather astonishing that this brain that essentially evolved originally in Africa to live on the plains and then has gone around the world, etc. But it's there for our survival, right? So Charlie Lineweaver at ANU has spoken about this thing. Is intelligence an evolutionary goal? And he basically says no. We are a fluke, right? We became intelligent because it helped us to survive. But that doesn't explain why we then could turn that intelligence to the universe and ask questions like, where did the universe come from? That's not really helping us in the survival thing. And we've done that in the last few tens of thousands of years. My worry is, of course, that there's a couple of things. Number one is that we have to, at some level, appreciate that there is a limited compute power up there, right? So you'll never outthink a true supercomputer in terms of raw calculations. But there is another ingredient: the consciousness, the ability to come up with new and novel ideas. And people are questioning whether artificial intelligence is going to have that ability. If artificial intelligence is ever going to have the ability to come up with something new, or will everything artificial intelligence do just be built on a theme that's been fed into it, kind of thing? And I really don't know. I've seen arguments both ways, but one of the arguments that does sort of freak me out slightly is this question of, if we do get a really smart AI and it does come up with the next level theory, that we will not understand it, right? Whether we will just not be able to comprehend what we are being told. And this is not a new thing, right? We've had this problem with computers in the past, in the sense that computers come up with solutions to problems, and we look at them and we just go, where did this solution come from? And even how does it work? How does the solution actually work? And it's only going to become murkier and murkier as the problems become more complicated and complex, etc. So yeah, we might have a computer that solves everything, and we just might not understand what it's telling us. And again, what do we do at that point? It might just look like gibberish to us, but it might be the theory of everything.
Yeah, I've had some kind of thoughts about that. I don't know if you've heard my spiels, but kind of the AI Einstein, or AI Galileo. I always have to have my finger puppets. You'll remember these guys. It's Einstein. So Einstein, I'm sure you've heard the story that he called the realization that someone in free fall would experience no gravitational force. He called that the happiest thought of his life. And of course, that led to the underpinnings of the weak equivalence principle, and from that comes GR, when you're married to special relativity and a lot of differential geometry and other cool things. When we talk about that, though, it's not clear that an artificial intelligent agent could have a happy thought. What does that even mean? And then B, visualize this free fall experience, which is kind of extrasensory and kind of revolves around a lot of experiential, almost wisdom, which by definition I don't think silicon agents can have, or even quantum Bose-Einstein condensate computers could have, or whatever you have. So in one sense, I'm more pessimistic about AI physicists, but I do share one thing in resonance with what you just said, which is could we recognize it or distinguish it from gibberish? So thinking about that question, I've often heard it said, Neil deGrasse Tyson, who was a guest on the show and hopefully will be back again soon, he says, if you don't believe in science, whatever that means, you're using a transistor right now, like you're talking to me on Zoom or, Zencastr or whatever, you're using an iPhone, you're like, so you don't trust the same people that looked into the laws of quantum mechanics and made that transistor, but now you think they're going to lie to you about X, Y, or Z. And I always have to kind of push back on it because I don't think anybody if you've ever seen the pictures of the first transistor, Bardeen and Shockley and others, not Cooper, blanking on the third guy. But anyway, they invented the transistor. It's like chewing gum and a coat hanger and a big piece of silicon, and it looks nothing like what you'd see in Schrodinger's equation now tells you what the how this device is going to perform. No, it's built from experimentation. Similarly, people will say, well, thanks to Einstein and E equals mc squared, we unlocked the power of the atom bomb. And you talk about this in your book, supersymmetry, string theory, whatever. If we do have a theory of everything, what will it do for us? And some people say, well, like it could unleash the equivalent of destructive power on the Earth that dynamite did compared to nuclear power, and then nuclear power compared to whatever the theory of everything will unlock. Do you believe that is a possibility? Like that merely the equations can actually lead to technology? I find them very separate. I find that distinction is very arbitrary. The people say because we understood because we understood evolution, we now have CRISPR. I think they're very different.
Yeah. So I don't have to tell you here, right? Science is a lot messier than the textbook portrayal, right? And the wash, rinse, repeat kind of idea that we wake up in the morning and the first thing we say to ourselves, today, what's my hypothesis, right? And off we go. We know that's not how it works. And we also know that, the experimentalists, they tinker and they play and they try and find things out. And it's a game at some level, right? But but it is a guided game in the sense that you do look at what other people have done and you think about how I could push an experiment this way or that way, etc. So there is sort of a relationship there. I do think equations carry power in themselves, in that, and this is what I say to my students, you may have experienced this, the transition of a student from like a student into a research student, when they stop, they derive an equation, then give you the answer.
Right.
But when they derive an equation and ask them what's the consequences of that equation, right? That's when they move into that research sort of area. Consequences come from examining the equations, and some of those consequences can be good, and some of those are not necessarily that good. E equals mc squared was definitely a driver in the development of nuclear physics. I think that's almost undoubted. But of course, at the time, even when E equals mc squared was published, I think it was Rutherford who said that anyone who says that you could get usable power from an atom is talking moonshine, right? Mm-hmm. So different people have different interpretations, I guess, of how powerful an equation can be. But I think it can be motivating. But as I said, science is a bit of tinkering over here, a bit of maths over there. Sometimes it comes together, sometimes it doesn't. But it sort of heaves itself forward.
Mm-hmm. Yeah, exactly. And I guess, I always like to, again, I want the readers to buy this book and read it in as many formats as possible. And I guess, the question is not maybe where the universe is coming from. That has to be answered. And I think, it's really that the title is really a descriptive. I mean, you go through here and you kind of gave me flashbacks to high school chemistry. You were going through Hund's rules and, how do you get these, the different packings, but you go through in really delightful detail on how the universe is really assembled, put together, if you will. And yet I think you do make this convincing case that there's a lot left to be discovered, and that we are kind of scratching the surface. And that, to some people is depressing because we spend so much time, so much money, it's so many people, we only have so much of all these things. And yet there are still so many mysteries left to do. But I think that's also what makes it exciting. And I guess if I had to ask you, of the questions that you pose and sort of put forth here, it's like children, you can never say, which one's your favorite. But is there kind of a bucket list question that you would like to ask the Almighty, or that you most are interested in understanding? I mean, you mentioned the weak force earlier, but could you put a spin onto, no pun intended, why that is, and kind of what the most ultimate satisfaction for you would be to answer in your career, or have answered in your career?
Oh, so in my career, so we are talking about very, very earthly kind of things. So I guess one of my driving forces in my research is, the dark side of the universe. That's the area that I think could be answered in my lifetime, at least part of it, right? So we know that we have dark matter, we have dark energy, and we've known about dark matter for rapidly approaching 100 years. If you look back at Zwicky's original work. Dark energy, theoretically for a bunch of years, but last 20 years, something is out there. I think that given the effort around the globe trying to answer these questions, that we will come to some sort of a conclusion, at least around dark matter, right? I mean, the particle physicists are going, full guns, the astronomers, and now the astroparticle physicists looking for signatures of what dark matter might be. Dark energy, I think, is going to be a tougher nut to crack, in that all the observations so far are pushing towards dark energy being maximally boring, in the sense that it's looking more and more like Einstein's traditional cosmological constant. And if that's what it is, then it's some background to the universe that we're never going to get to play with, we're never going to get to manipulate, we're just going to have to shrug our shoulders and say, it's there. But people are really looking for any signature whatsoever, that there's a deviation from that kind of simple picture. But the results out by the Pantheon people this week, we are heading towards a maximally boring universe. And that's actually one of my fears, right? Because after you've nailed down the equation of state to 5 decimal places, how much further do you go, right? 1.00 minus 1.000000. What do you do at that point? And we're not there yet, but it just feels like we're going down that road.
Yeah. No, that is true. And yeah, may it be, maybe you live in boring times on Earth at least, but perhaps cosmologically interesting times. So, Geraint, we've reached the end of the scheduled conversation, but there is a bonus portion, which I like to call the thrilling 3, the impossible questions, which I didn't ask you guys last time because it was 2 of you got, and I think it would be very difficult to ask 2 people, 3 questions each. So I would like to ask you some existential questions about where you have come from and where you are going, if you don't mind.
Let's go for it.
All right. So the first question has to do with your near-term future, although I hope not for 80 years or so. And when you reach the biblical ordained maximal age, as we scientists know, that's when our lives come to an end at 120, when the Rabbi Moses came to his end. You left an ethical will, kind of a bit of wisdom and intelligence. I see you as a seeker, as a thinker, not just kind of a technician. I think that you think big thoughts, and that's the kind of guest I love to have on this podcast. So I want to ask you this question: when you reach the biblical age of 120, what piece of wisdom, not monetary, not knowledge, what wisdom would you put in your ethical will to give as wisdom for future generations?
Oh, what wisdom! Oh my goodness. I think there are 2 bits and pieces. Number one, I really think it is be kind. I don't care what your occupation is around, and what country or clan you claim to be part of. I think be kind, and it's because I think we lose track of the fact that other people are people and they are dealing with their lives, and nobody's life is simple. But the other is to be curious. I do sometimes worry about the state of not just scientific knowledge, but the approach to science by governments, and that sets the scientific knowledge. And this notion of being curious for curious sake, to try and understand the deeper questions about the universe, I think is very important. There is more to life than just developing the next widget, the next iPhone, the next iPad. Answering these bigger questions, I think, is something that should be our goal as human beings.
You're speaking my language literally, because the motto of my YouTube channel is ABC, always be curious.
Excellent.
Okay, now I want to go farther into the future And this is going to take us along the lines of Sir Arthur C. Clarke's 2001 A Space Odyssey, where these monoliths make their appearance. I don't know if you've seen it or
Oh
not.
yes, yeah.
So these, we don't know what they are. Maybe they're time capsules. Maybe they're warnings. Maybe they're kind of, someone's putting it there to brag. But I want to ask a question as if they're time capsules and ask you what you'd put in it. Kind of a time capsule that you knew would last 1 billion years. And it's not too dissimilar from Richard Feynman's kind of what he called this cataclysm question. Like, what would you put what sentence contains the most information about the physical universe in the fewest possible words, so to speak? And he mentioned atoms. But I want to ask you, what would you put in a time capsule that summarizes everything we've learned about the cosmos? Not you specifically, but about humankind as a whole.
So again, that's a tricky question. That one is. I don't think I have a very simple answer to this. I think if I was going to leave a message to any future creature that found this capsule, I think it would be that we were proud that we've learned so much in such little time. And again, maybe we want a summary of what we know there. But I think the fact that us slightly evolved monkey brains have achieved so much in a few tens of thousands of years is something that we should be proud of. And again, as Charlie Lineweaver says, intelligence might be a rare thing in the universe, and it might be that we are freaky, that we've developed it relatively fast. So, yeah, I don't know if I could write anything down that a creature billions of years from now would go, oh, I didn't know that. But I think I would write down something about being proud about what we have achieved.
Yeah. That's very beautiful. And speak for yourself when you talk about monkey brains. Okay. Last question has to do with not your future or the universe's future, but your past. And this has to do with Sir Arthur C. Clarke's so-called third law, which is the only way of discovering the limits of the possible is to venture a little way past them into the impossible. Of course, that's the name of my podcast, Origin, Into the Impossible, which we take from Sir Arthur. I want to ask you, what mysterious aspect of life, perhaps as a scientist or not, perplexed you as a 20-year-old, 30-year-old, what have you, but now makes kind of sense looking back with the aid of time and space? What kind of advice might you give to that 20 or 30-year-old person to give him the courage to go into the impossible?
Oh, again, another question that I don't know if I don't know if I've answered any of my questions that I had when I was a 20-year-old to do with life. I mean, as a young man, I was bothered by the questions I think that everyone's bothered by. I am still bothered by the existence of consciousnness, and I don't know whether or not I should be bothered about it. And the other one, of course, is pain. When you realize that pain doesn't exist, right? Pain is not, it's a signal, right? It's your interpretation of that. And you sort of wonder, that makes now sense to me in terms of evolution, of why pain is what it is as a evolutionary survival thing. But then why other things feel painful, which don't necessarily help your survival, again, is a little bit uncertain.
Are you talking about faculty meetings? Or what are you talking about here?
Yeah, I'm talking about. I'm currently dealing with astropolitics at the moment, and it is very painful. I don't know. I think
you always knew you wanted to be a scientist?
No, I didn't. I almost fell into this role more than anything. I don't come from a scientific background. My father was a coal miner. I didn't know any scientists. I did enjoy science, and I guess one of the things that I would have told myself back then is to understand that we really do not know everything. Because often science was portrayed, you watch a scientific documentary, you read an article in New Scientist. Often it's about, oh, look, this is all the stuff we understand. And really what drives me now, of course, is that stuff that we don't understand. And I would tell my younger self, to seek out what it is we don't know. Don't just rely on what we're told we do know.
Hmm. Tell me, how did a coal miner's son grow up to be, from Wales, grow up to be a professor and such a good communicator and writer, especially? You're the only commonality between the two books of yours that I've read. So nothing against Luke or Chris, certainly, but you're the only common author between them. So how did a coal miner's son from South Wales become such a erudite scholar?
Let's see. I mean, I went to high school, and it was only in high school I discovered that I could do mathematics, and I enjoyed physics. And it was in high school, my fellow students were starting to talk about going to university. So I thought, well, maybe I should do that too. And so I went off to university, and I did physics and astronomy. I thought I'd do physics because I could get a job somewhere, and I did astronomy as out of interest. And I did well. And so, as I approached the end of my degree, somebody said, "Oh, are you thinking of doing a PhD?" And I went, "I guess I am." And I applied to do a PhD. So there was never a grand plan. It was more of an amble and accidental paths than anything else. And yeah, I never planned to be a professor.
You just randomly ended up at Cambridge and then SUNY Stony Brook, which is where I had my origin story, but that's a tale for another podcast. Anyway, Geraint, it's a thrill to talk to you. I hope we do get to meet when you come up over from down under. Perhaps this year will be the end of this pandemic, and we'll be able to meet finally and maybe do a live podcast in person at some point. That'd be a thrill.
That would be wonderful. Thank you.
Thank you so much. So tell folks where they can find you on and about the internet.
So I'm on Twitter at cosmic_horizons, and I have a webpage, www.geraintflewis.com, but I'm happy to answer questions on Twitter or even post it through the website.
As long as they pass the rubric of your previous book. Geraint, thank you so much. It's been a treat, and I hope we can meet up and do it again sometime soon.
See you soon.
Any sufficiently advanced technology is indistinguishable from magic.